Welcome everyone. In this video I'm going to share my power meter with you. So as you can see, we have a little bit crowded breadboard, and then we have a Peltier cooler attached to a heatsink. So this is the ADS1115 so it's a 6 ampere unit. I will use this as our load. It's not the best load because when it is under voltage or current, it will change its resistance, and therefore the load will not be constant, or the current will not be constant as long as the temperature stabilizes on the both sides. But for our measurements it will be perfect, or for demonstration purposes. So let's see what do we have here in the power meter. So of course the heart of this thing, or the brain, is an Arduino Nano. And then we have a 128x32 OLED display. And here we have an ADS1115 4-channel AD converter. It has 16 bits resolution, so it's quite good for precise voltage measurements. And finally, we have an ACS 712 current meter, and this unit is capable of measuring 20 amperes. And this works on the basis of the Hall effect. So basically in this small chip there is some sort of magnetic sensor, and the magnetic field created by the current passing through this PCB induces some sort of voltage, which we will measure on the output. Of course the current here not directly induces the voltage, before you would misunderstand it. But this is the very basic principle. So you apply a current that creates some sort of magnetic field, and the chip converts that magnetic field to an output voltage, which we will measure by one of the differential input channels of the ADS1115. So I will use this in differential mode, which means that we connect both positive and negative sides of our input to the input of two channels. So for example, we pair A1 and A0 together, and then we put the plus and minus on that, and then the other plus and minus will be A2, A3, and that's how we will measure the voltages. So one voltage or output voltage is created by this, so the voltage will be proportional to the current, and we have to calibrate that. So what we will do, I already did that, but I will show you how to do that. But basically we have to measure the output voltage of this device at several current. So we have to measure the current with some other devices, for example by a current meter. So we measure the current and we measure the corresponding output voltage, and then there will be sort of a linear correlation between these two values. And using the linear equation, or the parameters of the linear equation that we fitted on these measurement points, we will be able to calculate the current running through these 2 points. And what is interesting about this chip is that when you don't have any current flowing through these terminals, then the output voltage here is the half of the VCC that you feed. So for example, let's say we are using the 5-volt rail, and it is exactly 5 volts. Then your output voltage will be 2.5. And as you increase the current in one direction, and you have, let's say, positive and here and negative here, then the output voltage will be shifted, let's say, towards the VCC. So it will be somewhere between 2.5 to 5 volts. And if you flip the polarity, so you have negative here and positive here, then you get some voltage between 2.5 volts and 0 volts. So you shift the voltage downwards, and that's how you can take care of the polarity, basically. So this is how it works. And then we use the other two channels in differential mode to measure the voltage. But since I want to measure something which can go about the voltage of the AD converter, which is of course 5 volts, then we will use some trick. And this trick is a voltage divider. So in this jungle of wires, you can see two resistors and a capacitor. It's a small 10 nanofarad capacitor, and the top resistor in this voltage divider is 68 kilo ohms roughly, and the bottom is roughly 20 kilo ohms. So where you measure the voltage is between the two resistors and the bottom of the voltage divider, which is then connected to the ground, and the capacitor is of course parallel with the bottom resistor here, and you feed the voltage which is applied on your load to the top of this voltage divider. I will make a drawing of this setup and I will show you there more precisely, but that's what we do here. So that means that with 1/2 of this AD converter we can get the voltage of the Peltier cooler, and then with the other half of this device, with the ADS1115, we measure the output voltage of this, which is proportional to the current running through this. So what we have to do is we have to connect everything. And what we do, we know that to measure the current, we have to connect our device in series. So what I will do is that I will use this. This is, let's say, the positive lead or side of the Peltier cooler. So that will be directly connected to the power supply. So this is our power supply. And there I also put the voltmeter, if I can, there. And the next step is that now I try to simplify, think about the water analogy. So water or the current comes and then it goes through the device. So then the black wire comes out, and now we put this thing in series with this. So I need a screwdriver and loosen the things a little bit. So now we are connected to this thing, and then the voltage has to come out, let's say, if we talk in like simple terms. So now our circuit is closed, and one thing is missing, the bottom of the voltage divider, which is now here, this brown wire. So then I put that to the negative side, because basically we want to measure the two sides of the Peltier cooler for the voltage. So now this is connected. So first of all, I turn on this thing, the Arduino, by connecting it to a power supply, and see what we see. So everything is running, everything is shown as 0. I already did the calibration, and what you can see is voltage, current, both are in the SI units, so voltage in volts, current is in amperes, and then we have the elapsed seconds, and we have P as power, so voltage times current. So I turn on the power supply, and I apply something around 2 volts. So let me see. This is above a bit, but we have 2.6 volts roughly. But as I said, the temperature of this is changing, therefore the current running through this will also change, and the voltage drop will be different as well, so it's not always proper. But it's more simple if I measure the output voltage, and I also tell you what I see on the screen. So now I measure this, and you can see that 2.67, and you see it's decreasing or increasing, whatever, it's increasing. So what I see here, or you can see this display, but you cannot really see this display, and that is showing 2.7. So that's pretty much comparable with this. And then if I turn this thing into current mode, so now we are at 0, and I try to clamp it so you can see it. 0.65, and I see the same there, 0.65, 0.66. It's jumping because it's not so precise. But what you can do there is average like 10 readings and write that, so that will be more closer to this thing, or whatever you use as a confirmation. So you can see that this is a very, very simple circuit, but still it's very useful. For example, if you are using a Peltier cooler, then you can very easily measure the load which is going through it. or the power which is going through it, sorry. And then that's like a very simple task. So that's what we have here. And now I will go to my computer and show you what happens with, first of all, with the circuit, and then I will also show you the source code, of course, and try to explain it to you. So this is the drawing of the circuit. Sorry, it's not the best, but I tried to make it more or less clean and clear. But I explain everything, so you will be able to see what is what. So let's start from the, let's say, power supply. I could not find any kind of power supply for this software, so I used a 9 volt battery to illustrate the power supply. It doesn't matter, so of course we have a positive side and a negative side. So we start in this direction, so you just follow the red, and then we go in one side of the current meter, and then of course it comes out, and it is connected to the plus side of the Peltier cooler. So we just go like this, and then we go out and go back. So you will see that the current meter is connected to the circuit in series, and then of course the VCC goes to the plus 5 volt, and the GND is obviously the GND, so you can find it on the breadboard, and the out goes to the A0 of the ADS1115, and of course the A1, which is in differential, so these are like one channel. The A0 goes to the GND, so you can see it here. And now, as we are here with the ADS1115, I just quickly explain it. So the VDD, of course, goes to plus 5 volt, and the GND is connected to the address, and it goes to the ground. And it's really important to connect this to the address, the ground, because this is how the Arduino will find this. Because, for example, you can have four of this ADS connected to the same Arduino in parallel, and you just have to connect the address to different pins. One pin is the VDD, and then GND, and then SCL and SDA, and that's how you distinguish the 4 units. So this is very nice. This alert is just skipped. We don't care about that. And then here is the already mentioned A0, and here is the already mentioned A1. So we are done. And now we try to measure the voltage on the same Peltier device. So for that, we basically use the AD converter as a voltmeter, and we also add a voltage divider. I draw it here somewhere because it's more easy to visualize it. So basically, we imagine our Peltier cooler as a resistor. So this will be, I just put a P here as the Peltier, and then of course this is just the power supply now, but we don't care about that. And what we have here is the following. So we have a junction, of course, and then we have a resistor here. This should be the 68K, and then we have another resistor which should be the 20K, and we go back to this. And what happens here, that we go out towards the A2 and towards the A3, but at the same time we put a 10 nanofarad capacitor here, and then what happens here is the whole thing is just connected to the GND. So this is our setup for the voltage measurement. So you can see that one current goes in this circle and another in this, but this is like very negligible, so it doesn't really disturb this. And you know that this voltage here is basically this. So now we have Vp as the Peltier times the R2 this is a plus. So basically what we do here is we will see that what is the V out, and we will get something, let's say if the voltage on the Peltier device is 20 volt, and then we have our devices, and here comes the trick, and you have to be very careful. You don't just pick a resistor from your drawer and say that, okay, this is the 68 kilo ohm resistor, I just put it in my circuit. Measure it. You have to measure it and see what's the perfect or exact value. So let's say in my case this was 67.16 kilo ohms, and then here I had again, right, 67.16k plus I measured this again. You have to measure the physical value of it, 19.76k. Otherwise you will have some inaccuracies, and then you do the math, and then you get this. So this means that if there is 20 volt in this branch of the circuit, then the voltage between A2 and A3 will be 4.5, and this is very let's say comfortable for us, because the maximum voltage which you can measure with the AD converter is like 5 volts. So this is like a safe limit, because I know that I will not run my Peltier units about 20, not even about 18 volts, but let's say about 20 volts. So then we will never reach this value. And now what you do is just a division. So basically you divide 20 by 4.547, and you want to use several decimals here, so 4.39850. So when you read the value of the bits which are coming out from the ADS1115, you have to use this as a multiplier. So your real voltage will be the conversion between the bits and the voltage, the output voltage, times this. I will show you this exactly when I show you the source code, but this is very important. But once again, so when you try to design your voltage divider, you have to see that your maximum expected voltage in your circuit that you try to measure should not create higher voltage on the output of the voltage divider than the voltage that your ADC can survive. So let's say that whatever the voltage here should not create higher voltage here than 5. And then you choose this accordingly. But you have to be a bit careful, because sometimes these AD converters or some other units that you can that you want to use for signal processing or whatever have different inputs. And for example, this has a somewhat high input impedance, and if you choose your values too high, so for example you are in the mega ohms region, then it might be the case that you don't get sufficient voltage showing up on these two outputs, and that can lead to some funny numbers. I previously used 3 and 1 mega ohms, and that was horrible, because when I went up to a certain voltage value, I just could not measure properly, so my numbers just flipped, and after a certain voltage everything turned into negative, and I don't really know the reason, and I just suspect that maybe it's because of the high input impedance. But now everything seems to work. So now we know that basically I just drew this thing here, and now we know how this is connected. So this is the top of the voltage divider, and that goes to the positive side here, and then this is the middle where we take our measurements. So what you have to see here is that this is the bottom of this first resistor, so this is the 68k, and then the top of the next resistor, which is the 20k, and you see that this goes to the A2, and we have our capacitor here and between the ground, and then now we move down to the ground, so we are here, and nicely everything is connected here. So you see that the capacitor's negative side, and then we have the common ground here, and this goes to the ground, and we go back with a wire to the negative side of the Peltier cooler. So this is how we measure the voltage across it. And you saw it in the demonstration that the multimeter pretty much showed the same voltage as I measured with my device that you see here as a drawing. So you see that this works, and it's fairly simple, but you have to be a bit conscious about these values here. And also, don't forget this guy. You need that. And just the last part here. So this OLED display. So we have the GND that goes to ground, and VCC that's +5, of course. And we have the SCL, and that is connected to the SCL of the ADS, and then they go together with to the A5. So that's quite obvious. And then we have the SDA of the two devices. So the ADC's SDA is connected to the OLED display's SDA, and then they go together to the A4. And that's all. So this is the complete circuit, and you can see that it is fairly simple. And then we can measure 20 amps and 20 volts maximum. So this is what I can do right now. I could choose other values for the resistors, and then I could measure maybe higher voltages, but this is just fine for me. So now let's see how the source code works. So this is the source code, and it's very, very simple. So here I'm defining the things for the OLED display, and as you can see on this library that I'm using the ASCII based library, and I cannot emphasize enough that you should use this if you are using the Arduino Nano and you just want to display some text, because the other, let's say, default library is eating up all the memory, and you will not be able to use your device for anything else, just to display something on your display. But you cannot display any values or some details from your measurement, because then for that you should write more code, use other variables and stuff like that. And if you use the default library, that doesn't really allow it, because the hardware is just not that good of this Arduino Nano. So just use the text-based library and you will be very happy. And then we use this Adafruit library for the ADS. We create an instance, and then we want to measure the time. So we have a start and elapsed time. And what I want, voltage, and then raw current. That's just some value for myself to use the raw data which is coming out from the current meter. And then this is the variable for the current and for the power. And in the setup, we just start the serial port, because we also want to receive the data from or through the serial port, and just some random message, so we see that the device is started. And this is just some comments, but it's very useful. So what you can see here is that you can change the gain settings of the AD converter, and with different gain settings you get different ranges for the voltages, but for that you have to use different multipliers. That's all. You can also define the speed, but that depends on your library, because some libraries don't know these set SPS command, so you just skip over that. And then here I just set the gain to 2/3, so I'm just using the maximum here. I don't need really high resolution. And here we just take care of the OLED display, nothing fancy or nothing interesting here. And I was just playing with the reference voltages, so this is not really important. I can skip this. And we start the timer. And you see that our loop, the main loop, is very, very clean. So we measure the power and also all the details. So I created a function for this. And we print the details to the serial port and then to the display, and we wait half a second. And then we go over and over. So here we note down the elapsed time. So this will be the time difference for our first measurement. And then we create the voltage. So if you remember this number, this is what I calculated at the previous image where I showed you the voltage divider. So basically this is the division factor. So for example, if you measure something which gives 20 volts, then you measure the 4.5 something volts. And if you divide the two things, then you get this number. So basically, when you go the other way around, you have to multiply your result with this. So you know what is the real thing, the real voltage that you are measuring. Because this, without this, you get the voltage which is measured on the output of the voltage divider. But if you use this multiplying factor or division factor, then you know what the voltage divider sees on the other side. And then we use the differential mode, so we read the voltage on the number 1 and number 0 pins. And then this is just to create the bits into millivolts. So the number, the output of the ADS times 0.1875 will give you the number in millivolts. But I don't care about millivolts, so I divide it by 1000, and that gives you the result in volts. Done. We go to the current. So how we get that? We have to get our values in millivolts, and then we have to subtract this 2309, and then we take the whole number and divide it by 92. And this is basically what I explained. So by default, when you have the zero current through your device, then you are somewhere around 2.5 volt. So now we shift it back to 0, and then we divide it by roughly 100, and 100 is roughly the division factor, or the, let's say, gain of this kind of current meters. So this is how you measure basically, and this was basically the output of my calibration. So when I plotted the current on the x-axis versus the voltage on the y-axis, and I fitted a slope on it, or linear equation, then this was the B and this was the A, and I just rearranged the equation, and this is what I got from it there, from the equation. And then here we just calculate the wattage, so voltage times current, and then we have the three variables that we wanted to get. So I just print the time in seconds, and then I print the voltage with 3 decimals, print the current, and print the power. And then I do the same, but now not at the print serial function, but on the OLED display. So first clear the display so that gets rid of the previous numbers, and then put the cursor into the 0, 0 position. And you have to remember that this cursor is now moving pixel by pixel and not block by block, as in the case of this 16x2 LCD display. So yeah, then we print the voltage with 3 digits, the current with 3 digits or decimals, sorry, and then we move to the second line, and time and the power is being printed, and then this just repeated over and over in the loop. So basically this is the whole code. It's very, very simple, and you see that you can get very nice results. Two things that you have to measure is the values of the resistors in your voltage divider, so you get this division factor precisely, and you really need to be precise here. So it does, I mean, it's not enough to say that it is 4 or it is 5. No, it should be 4 point something something. So then this is the first thing that you measure, and then you measure the current versus the output voltage of the ACS 712 current meter, and basically that's all. You fit the slope on it, you get the parameters from the linear equation, and you just rearrange and substitute here. So that's all. And I will use this device in my other projects, for the Peltier cooling projects, because I also want to log the voltage and the current which is flowing through the device or applied on the Peltier device. So together with all the temperatures, now I will have all the power values as well. So that will be like very useful for me. So I hope you liked this video, and I hope it was useful. And please give some comments if you have something, if you discovered some mistake or just have some question or something like that, just let me know. And don't forget to subscribe, and see you in the next video.